Very good morning, dear students. So, in this session, we will study the characterization of biomass. So, I will you distinguish different biomass based on energy production, and this is done with the help of a number of properties. A number of properties are used for identifying its capability of energy production. We cannot use every biomass for energy production. We have some criterias and we have different routes for energy production. We know that we can produce energy by gasification, by incineration, by anaerobic digestion. A number of routes are there, and which route we have to go for is depending upon these properties. So let's see what are the important properties used for characterization of biomass. First, we have a number of physical properties. The important one is density, then particle size and size distribution, and another important physical property is permeability, which is also known as hydraulic conductivity. Then moisture content is there. So these are the important physical properties used for characterization of a biomass. Then chemical properties, we have very two important properties, that is proximate analysis and ultimate analysis. So this should be done before selecting a biomass. Proximate analysis and ultimate analysis. This is very important. Then another chemical properties is fusing point of ash and lignocellulosic composition. So every biomass is made of lignin, cellulose and hemicellulose, and which will depend upon which part of the plant we are using. For example, leaf, we have a particular lignocellulosic composition, but its stem will be a different lignocellulosic composition and other parts will be different, and it's also vary from plant to plant. And this is very important for anaerobic digestion, biogas formation. The lignin content should be very less. If the lignin content is very high, these bacteria will not be able to digest this biomass. So in that case, this is very important, the lignocellulosic composition. And finally, we have energy content. So energy content is the calorific value of that biomass. So from that we will be able to get what will be the calorific value of our output gas or liquid, etc. So these are the important properties. So in this session we will cover physical properties and chemical properties up to proximate analysis and ultimate analysis. The remaining we will cover in the next session. Now all of you know what is density. It is the mass by volume expressed in kilogram per meter cube. But in powdered biomass, so we have some powdered biomass like sawdust, coir pith, etc. These are in powdered form. We have three densities associated with it. So what are these three densities? The first one is absolute density. So what is absolute density? It excludes the volume of pores and interparticular space. So if you are not considering any pores, for the volume between the pores and also other interparticular space, it will be the absolute density, and it is the true density. So this is very difficult to determine. We have to use some scanning electron microscope or some other costlier equipment, because we have to avoid all the interparticular space and pores, etc. So this is absolute density. Then another one is envelope density. So in this, interparticular space is excluded, but it includes the pore volume. So pore volume they are including, but interparticular space they are excluding. So like that we can determine the density. So that is known as the envelope density. It is also known as apparent density. But this is the most important one. We will be mostly using bulk density, also known as BD. So bulk density includes both pore volume and interparticle space. So we don't have to bother about pore volumes or interparticle space. As a whole, we are determining the density. So that is the bulk density. So mostly we will be using bulk density. And the measurement of density is normally carried out using a small equipment or device known as pycnometer. So this is the pycnometer. So simply we will use Archimedes principle. We will have some reference liquid and we will put our biomass, and that volume change we will measure, and we can also measure the mass of that sample using some my weighing machines, micro weighing machines. So with that we can determine the density. So it works on the basis of Archimedes principle. So you can refer for further details. So this is the instrument pycnometer used for measuring the bulk density of biomass. Then another important characteristic is, even though the density is different, if the particle size and its distribution will affect the energy production from biomass. So particle size means how much micrometer is that diameter of that particle. So if you are using sawdust or coir pith, etc., or if you are using cockle shell, it will have different diameters. So it distribution also important. So suppose we have 10 micrometer to 50 micrometer, 20% is there, then remaining 50 to 100 we have 30%. So that is the distribution of biomass particle size. So both are important, and the journals literature we can see that especially gasification, combustion, etc., will depend upon this particle size. When the particle size is smaller, it will be, we will have a better gas or combustion products, and they are determined with the help of this sieve, trommel, or particle size analyzer. The sieve is used in civil engineering laboratory, geotechnical lab. We have different filters of different size. So our biomass will be put into this and it will be stirred. So after stirring, this will settle in different layers of these filters, and each layer we have a particular mesh of diameter. So using that we can identify the particle size and distribution. The trommel is also very much similar, but its filters are on the periphery of this device. And if you want more accurate particle size distribution, we have to use the particle size analyzer, which use the camera, this high contrast, high resolution camera and other modern sensors, etc. So we have, but mostly we will be using this sieve analysis for determining the particle size of our biomass. Then hydraulic conductivity or permeability, that is also important. It is a measure of ability of a porous media to conduct liquid. So it is important when the biomass is porous structure. So how much water it can, or how much liquid it can move through that biomass, it is known as the hydraulic conductivity. And even though the hydraulic conductivity testing is simple, it will depend upon a lot of things. For example, the factors affecting hydraulic conductivity, we know the particle size. The particle size will affect the hydraulic conductivity. The fabric nature of our biomass will affect. Then degree of saturation. So if already there is a moisture content in that biomass, this hydraulic conductivity will be less. And if it is a very dry biomass, hydraulic conductivity will be more. So that is known as degree of saturation. Then pore geometry. Then our test fluid property will also depend on this hydraulic conductivity. So, but this is not that much important. It's mostly important in soil testing and soil preparation. But still, we can use this property also for distinguishing a biomass. So this is hydraulic conductivity, which is also known as permeability. And the most important one we are getting into that is proximate analysis and ultimate analysis. So in any biomass related journal, in that if you are using biomass for energy production, you must find out the proximate analysis and ultimate analysis for modeling of biomass gasification, modeling of all other energy production routes. We require this. So what is proximate analysis? It is a determination of moisture, volatile matter, fixed carbon and ash in a biomass. So its total will be 100. So these are expressed as percentage. So these are the four important elements in a biomass. So every biomass we can split into these four categories. One is moisture. We know that a different biomass will have different moisture content. Then another one is volatile matter. That is how much gas it is content is in the form is trapped in that biomass. So that will go out when the temperature increases. This volatile matter will escape into the atmosphere. Then fixed carbon will be mostly converted into char, solid char, known as biochar, and ash is there, ash content. So all these constitute the biomass structure. So our biomass will have different levels of these four categories. So how we are going to determine these four? For that we require a furnace, a muffled furnace and a hot air oven, etc. So how the moisture is determined? It is very easy. We have to take a known mass of biomass and heat it in a furnace or a hot air oven at 105 degrees Celsius for 24 hours. Then again the sample is weighed and we will see some mass is reduced. So that loss in mass we will take as moisture. So that is a simple procedure for determining moisture. So what we have to do is, suppose we have to take some 5 gram of biomass. Before testing we have taken 5 gram of biomass. We are putting it in a hot air oven or furnace, set the temperature to 105 degree, and we have to keep it there for at least 24 hours, that is one day. And after that we again take that out. We will see some mass is reduced. Weigh the final mass. Suppose it is 4 gram now. So that means 1 gram was moisture. It is escaped into water vapor. So our moisture content of biomass, initial moisture content of biomass will be 1 by 5 into 100, that is 20%. So like that we can identify the moisture percentage of biomass. So we have to use a furnace or hot air oven. Then volatile matter is the sample. So after determining the moisture we have to determine the volatile matter. So these have to done in a step by step. First we have to determine the moisture, then we have to go for the volatile matter. So our sample after moisture determination is ignited in a muffled furnace. So we have again used a furnace, and but temperature is now very high, that is 950 degrees Celsius for 7 minutes, and in the absence of oxygen in a closed crucible. That is important. So otherwise this combustion will take place. If oxygen is present and if you are using high temperature, it will be converted into its combustion. But we don't have go for combustion. We have to should be carried out in the absence of oxygen. That is very important. So we have to use a closed crucible. So our sample after moisture determination is taken in a closed crucible so that there will be no oxygen. Put it in a furnace, muffled furnace. Keep the temperature 950 degrees Celsius for 7 minutes. So what will happen? These volatiles will escape. So again weigh our sample. So it will be again reduced. So with that initial and final mass, in this testing we can determine the percentage of volatile matter. So everything is expressed as percentage. Then ash. So after these two tests, so after moisture and volatile matter, so dry sample, after this first and second test, we will be again igniting in a muffled furnace, but this time we will be using in the presence of oxygen, and the temperature is 750 degrees Celsius, half an hour in an open crucible. So here we are burning the biomass. Combustion takes place in the presence of oxygen in an open crucible. So what will happen? So biomass, very biomass will be converted into some gas, and the residue left will be ash, and that weighing that mass we can determine the ash percentage. So in this third test we are burning the biomass in the presence of oxygen at 750 degrees Celsius for 30 minutes, and the residue left after this process will be the ash content. So that is the method for determining ash percentage. So after this all three, we don't have to go for any test for fixed carbon. This can be obtained by subtracting 100 minus all other three quantities. So that is, there is no separate method for determining fixed carbon. So it is determined by 100 minus adding all other three: moisture, volatile matter and ash. So this is the way we are using for finding out. So it is a step-by-step procedure with the help of crucibles, open and closed crucibles, and different temperatures, and with the help of furnace only we can determine all these three or four properties. So this we have a small problem. We can understand more about this proximate analysis. So before that, these are the proximate analysis of samples, some commonly available samples. You can see here coconut shell. This will be different for different location and drying conditions, but this is a typical example. We can see coconut shell. If you take coconut shell, it's almost 5% we have the moisture. Ash is very less. That is the advantage of coconut shell. Mostly it will have volatile matter, very high volatile matter, and fixed carbon is 22%, volatile matter 71. But in the other hand, if you use rice husk, we have rice husk coming from rice factories. This moisture content is little bit high, 11%, 11.2. Ash is also high. That is a problem with rice husk. So if you are using rice husk for gasification and other energy production, the ash will be very high because it is having a 18% of ash content. Then volatile matter is 48.31. Fixed carbon is 22, again around 22. Now municipal solid waste, the waste we are coming, domestic waste coming from our household, is approximately moisture is 21%. So high moisture is there. Ash is also 20. The volatile matter is 52, but only you can see the fixed carbon is very less, 7% only. And food waste, mixed food waste coming from restaurant and other large cafeterias, it's very high in moisture content. You can see the mixed food waste is having a moisture of 70%. Ash is 5, volatile matter 21.4, fixed carbon 3.6. So this type of biomass where moisture is very high, we cannot use it for gasification, incineration, etc. The only possible route is anaerobic digestion, that is biogas production. So that is the important criteria we have to understand. So biomass moisture content is very high, like this mixed food where 70% of content is moisture. We will not be able to use it for gasification or combustion, etc. We have to go for anaerobic digestion, that is the biogas production. But on the other hand, if you see coconut shell, its moisture content is very less, and it's have a good volatile matter and carbon content. We can use it for gasification or bio other combustion, etc. So that is the main property. Moisture, we have to look into it. If the percentage is very high, we have to go for anaerobic digestion. Finally, you can see the mixed plastic. It's a very less moisture content, 0.2, but the ash is very high. So the plastic also is not that much suitable for energy production because it's ash percentage, but this will be different for different plastic, different plastic for PVC, different plastic will have different properties. But this in this case it's a very high in ash content and less in volatile matter and fixed carbon, so it is not that much suitable for energy production, but it will be better to go for some pyrolysis or some other treatment so that we can convert this into some oil, bio oil. That is in the case of mixed plastic. And we have a very good database, that is Phyllis, a Netherlands website, phyllis.nl, where you can get these proximate and ultimate analysis of biomass samples. They are taken from different journals. They have a different one biomass also, they will have slightly different values from. All these are taken from journals and other important work, so you can use that because this proximate analysis we cannot do in our laboratory because we require a furnace, very high temperature is also required. So if that is not there, we can take this data from journals and this database phyllis.nl. And we have a small problem to understand more about this proximate analysis. See, the 1 gram of biomass sample is heated at 105 degree for 24 hours, and the weight of dry material is found to be 0.9 gram. It is further heated in a furnace at 950 degrees Celsius for 7 minutes in the absence of air by putting a lid of the crucible. The weight loss is found to be 0.3 gram. Then the remaining material is cooled with the lid cover and the temperature is reached to the ambient temperature. The lid is opened and is further heated in an oven at 750 degrees Celsius for half an hour in the presence of oxygen. And after cooling, the material residual mass is found to be 0.14 gram. Determine the moisture content, volatile matter, ash and fixed carbon of this biomass waste. So this is a typical numerical example of how we are going to determine this proximate analysis. So we have taken 1 gram of biomass. So you can see the step-by-step procedure. First we are considering the moisture determination. For that it is heated in a furnace of 105 degree for 24 hours and the weight is reduced to 0.9. So what will be the moisture percentage? So after moisture determination the weight is 0.9, so that means 0.1. Initial mass of biomass is 1 gram. The moisture content will be 1 minus 0.9, that is 0.1 was the moisture, and that in 1 gram. So that means divide by 1 into 100. So 10% is the moisture. So denominator we have to take 1 itself because we have taken 1 gram of sample. And the difference in mass is 0.1 gram. So 1 gram is reduced to 0.9. So our moisture percentage will be 10%. Then after that we are determining the volatile matter. It is heated in a closed crucible 950 degrees Celsius for 7 minutes in the absence of oxygen or air. Now what is the new the weight loss? 0.3 gram is lost. So 0.9, already it was 0.9, now 0.3 gram is lost. So it is reduced to 0.6 gram. So volatile matter will be directly we can say 0.3 divided by 1 into 100, 30%. So 0.3 gram was the reduced mass in second step, which represent the volatile matter. So it will be 0.3 divided by 1 into 100, that is 30%. And finally ash, after that test we have taken the sample again, we have opened the crucible lid and air is allowed to pass. Again temperature is reached to 750 for half an hour. So it is after burning we have combustion takes place, then the residue is ash and its mass is 0.14 grams. So our residue left after the third procedure is 0.14 grams. So what will be the ash percentage? It will be 0.14 divided by 1 into 100, it will be 14%. So that is the ash content. And finally fixed carbon, we have to subtract this 100 minus 10 minus 30 minus 14. So every other three content we have to subtract from 100. It is found to be 46%. So this is a simple steps we are undergoing for determining the proximate analysis. Now ultimate analysis is most complex and elemental. We have to determine the elemental composition of biomass along with ash. So what are the important elements? Carbon, hydrogen and oxygen are the major components. CHO, carbon will be present in every biomass. Hydrogen also will be there. Oxygen will be there. And along with this we have some trace elements like nitrogen and sulfur. It will be very small quantities. Sulfur etc. will be very less. In some biomass it will be zero. So this is a very important property. Another important property is with carbon CHONS. We have to determine the percentage of that elements in that biomass, because this will depend what will be the gas we have produced after gasification from that biomass or combustion from that biomass. This is necessary. So if we have a more carbon content means it will have a capability of more carbon monoxide and carbon dioxide, and if we have more hydrogen means the water vapor will be more or hydrogen gas will be more in the product side. So like that we can predict the composition of gas or a liquid which is producing from this biomass with the help of this ultimate analysis. So it is also very necessary, and it is determined with the help of an instrument. It's a very costly instrument, that is CHNS analyzer. It will be gas chromatography also we are using in this CHNS analyzer. So this is not like the proximate analysis where we can manually calculate and find out these important constituents with the help of furnace, but here we have to use this CHNS analyzer. The principle of this is we know all the atoms prefer to be in their oxidation state. So if you are supplying the oxygen and a high temperature around 990 degrees Celsius, what will happen? So we have our biomass, we have taken our biomass and we are supplying enough oxygen with high temperature. It will be converted into, so we are simply gasifying our biomass, that is it will be converted into carbon dioxide. Carbon will be converted into carbon dioxide. If you are supplying sufficient oxygen, there will be no carbon monoxide. It will be, that is complete combustion. It will have carbon dioxide. Similarly hydrogen will be converted into water vapor and nitrogen will be converted into NOx or nitrogen gas depending upon the temperature we are giving. So we have in this CHN analyzer we will be supplying oxygen and we will be using high temperature to convert this into gas, carbon dioxide, water vapor, NOx, SO2 etc. gas. Then we will measure the percentage of this gas in that and we can find out the elemental composition of these elements in biomass. So that is a step we are following. So for this the product gas mixture flows through a silica tube packed with copper granules. So first the gas is flowing. So after the gas is produced we have to determine the composition of this gas. So in CHN analyzer first we are converting our biomass into gas, CO2, H2O, vapor and other gases with the help supplying oxygen and high temperature. Then this gas is flowing through the silica tube packed with copper granules its temperature is around 500 degree, and in that we are nitric oxides are reduced. So in that first step we can determine the nitric oxides. Then that gas is again passed through different traps like SO2 traps, and other gases are eliminated step by step, and we can determine the percentage of that gas in that product gas. So that is the step we are following. So for this we have to use a carrier gas also, because we have to carry this product gas through different sections. First we have combustion takes place, our biomass is combusted, and that gas is to be carried out through reduction zones, mixing zones, separation zones, and finally we have to detect that. So we use a carrier gas, and mostly we will be using helium. High purity helium is used as a carrier gas, and these are passed through the gas chromatographic system. So after these different steps we are passing this to a gas chromatography. So gas chromatography, different techniques are available. Gas chromatography based on infrared absorption techniques. So it's a vast area. You can refer more about gas chromatography. And the what we will get is, in gas chromatography we will get the signals, step by staircase type signals like this. So our output of gas chromatography will be a signal like this, a staircase type signals, and this height of this step is proportional to the amount of that gas. For example, in this all of them are represented as equal height. So that means the nitrogen, carbon dioxide, H2 and SO2 are in same, almost same proportion, but actually it will be a different step height. So that we have to interpret with the help of some softwares and other inbuilt data. So that is gas chromatography. Gas chromatography is the technique used for finding out the composition of a gas. It is the most accurate method available. So our output will be like this, a staircase type signals we are getting. We have to interpret its percentage from this diagram. So that is about gas ultimate analysis. So ultimate analysis is not that much easy like proximate analysis. First we have to combust the gas sample by supplying enough oxygen and temperature. Then that product gas has to pass through different sections, different separators, different reduction zones, and we have to determine the gas composition with the help of gas chromatography. Then with that we can identify what is the percentage of carbon, nitrogen, oxygen, etc. in our biomass sample. And this is the typical ultimate analysis of some samples. This is also taken from Philips database. You can see coconut shell is having a carbon of 49%, hydrogen is 6.2, oxygen is 37, and nitrogen, sulfur, you can see in every sample it will be very less. If you can neglect, we can neglect that, because the nitrogen sulfur content will be mostly very less than 1 in most case. And rice husk, you can see carbon content is not that much high compared to coconut shell. Its carbon content is only 27.9, but its oxygen content is very much near to, this is ash, due to ash. So in beside this we have ash also. In combustion, after combustion the residue left will represent ash. So that is also we have to add to get 100%. So rice husk we have this low value, the remaining will be ash. But coconut shell we have ash content is very very less, so that is why we are getting this high carbon percentage and oxygen. Then municipal solid waste also have high carbon content and oxygen content. Mixed food very high in carbon but it's having less oxygen. And plastic also we have 60% carbon and 22% oxygen. So carbon and oxygen is very very important. Hydrogen also will be there in considerable amount, but nitrogen and sulfur we can neglect. So this is about proximate analysis and ultimate analysis. So next class, next session we will cover the remaining properties, that is lignocellulosic composition, is fusing point of ash and the heating value of biomass. So thank you.